So when you're trying to multiply large numbers, if you're familiar with the exponent laws, it makes the task a lot easier. 1,000 is basically 10 times 10 times 10. So you can rewrite it as 10 to the power of 3. So if you multiply 10 to the power of 3 times, you simply add the exponents, you get 10 to the power of 9. So 1,000 times 1,000 times 1,000 gives you 1 billion. And another way of writing 1 billion is to say 1.0 times 10 to the 9. You're multiplying by 1. It's still the same thing. That would be called scientific notation. That's just showing it as an exponent. And if you write out the whole number, then you just have 1 with 9 zeros after it. Either way, they're all the same. If you have, sometimes you'll see something like this, where they have a number next to a radical sign. You know square root. Square root, for example, implies that it's a 2 in there. So square root of 4 gives you 2. What if you have a cubed root? That means the question they're asking is, what number multiplied by itself 3 times will give you the number that's under the sign? And that would be 2, because 2 times 2 times 2 gives you 8. So it's a good idea to memorize a few cube roots, because it gives you an insight onto, say for example, if you're given the volume of a cube, you can, if you know all the cube roots, assess how tall the cube would be. So I recommend you memorize these. You should memorize 1 cubed to 10 cubed all the way. I'll just write them down for you, so you can, when you see them, you can recognize them. There's a funny story told about a famous mathematician. His name was Srinivas Chandrakasar, if I'm not mistaken, and he was sick. I think he had tuberculosis, and he was being visited by a professor who was also a mathematician. And mathematicians like to ask each other nerdy questions to see if the other one is just as smart as them, or they play around with numbers. And the mathematician said to him, "So, what was the number of your taxi cab?" And the other mathematician said, "It was a boring number. It was 1729." And Srinivas says, "Not true. 1729 is the smallest number, which is the sum of 2 cubes." What? So I'll show you what he meant. It came to be known as the taxi cab number because of a nerdy joke between 2 mathematicians. But his insight was instantaneous. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed, which means 4 times 4 times 4 gives you 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1,000. So the taxi cab number is the smallest number, which is still the sum of 2 cubes. So 10 cubed plus 9 cubed gives you 1,729. Did somebody just check 9 cubed? Because I may have gotten that one wrong. 9 y to the x, or second function cube, gives you 729. Okay, I got it right. So 10 cubed plus 9 cubed gives you 1729. But you know what? 12 cubed is equal to, I'll just throw that as an aside. I didn't ask you to memorize that far, but it's 1,728. So 12 cubed plus 1 cubed also gives you 1,729. So this is the smallest number, which is still the sum of 2 cubes. And the insight of this Indian physicist, who later on developed some theories that helped scientists prove the existence of black holes using mathematics, because you can't go to a star and make measurements. Whatever measurements we make from planet Earth. We have never gotten past the moon, with manned missions anyway, and we've never gotten past basically our solar system. So we're just barely outside of our solar system as we speak. There's 2 Voyager spacecraft that have been launched into the void, and they barely made it out of our solar system. So they're not even They're not even getting there to the closest star. The closest star is still thousands of years away. So the distances in our solar system are just so large that they beggar the imagination. We can't get our heads around how big the universe is. Even our own galaxy. Only 100 years ago, scientists thought that our galaxy was the whole universe. And then they started developing better telescopes, and they said, hey, some of those stars look fuzzy. Why did the stars look fuzzy? When they zoomed in, they realized, oh my gosh, it's another galaxy with 100 billion stars in it. So what looked like little fuzzy stars were actually entire galaxies composed of hundreds of billions of stars. So as the science progresses, we are become aware of new things. But only 100 years ago, we thought the Milky Way was it. We didn't know. Now we know that the universe is a lot bigger than we thought. It's very humbling. The next thing I'd like you to be familiar with is how to convert the prefixes that we use in the metric system. I have an example here from the textbook that I normally use. I'm going to see if I can append this textbook because I have it online. I don't know if I'm able to put it I'll try this afternoon, and that way you can get chapter 1 so you can give it a read through if you're interested. So, what is the name given to the unit that equals 10 to the minus?
Good morning, staff and students. I'm sorry for the interruption. Could all teachers please complete and submit the Google form to Mr. Silva sent out yesterday? We have the technician in today and would like to submit this information. Thank you.
What Google form? But you're all into the system, right? You all see in the profile? Yeah. Yeah, it's a good idea, but I think the blind isn't there. It fell off. Look at the ceiling. Is it there? No. So that's why it's not closed. Otherwise, I would have closed it because it creates a glare on the board. You know what you can do maybe is put some of these boards up there just to block some of the sunlight. Just rest them on the windowsill. It'll decrease it a small amount. Put 3 of them there. I'll do it for you. And you know what? With this, it's even better. That better? Is it better with the lights on here?
Good.
No? Makes it worse? All right. So, I was saying that they want you to convert 10 to the minus 12 of a second, for instance. Okay? I'll read you a question. What decimal fraction of a second is a picosecond? B, express the measurement 6.0 times 10 to the 3 meters using a prefix to replace the power of 10. C, use exponential notation to express 3.76 milligrams in grams. So this is practice example, page 15 from the textbook I normally use. Picosecond equals 1.0 times 10 to the negative 12 of a second. It's 1/trillionth of a second. There is actually some use for such short intervals of time. Actually, they even use shorter than that. They use femtosecond laser spectroscopy to determine the mechanism of certain molecular reactions. And there was actually a professor who does that in the University of Toronto. He won the Nobel Prize for doing research on precisely that use of super fast flashes of light to find out what molecules are doing. Femtosecond laser spectroscopy. His name is Polanyi. I don't know if he's still alive, but he was He's our local genius in Toronto. You could also say it's 1 over 10 to the 12 of a second. So it equals 1 trillionth of a second, 1 with 12 zeros as a fraction. It's a very short period of time. The next one is they ask you to convert 6.0 times 10 to the power of 3 meters. So you can rewrite it as 6.0 times 10 to the power of 3, times 1,000, because that's what 10 to the power of 3 is, 1 with 3 zeros. Or you could say 6 times 1,000, which is 6,000 meters. Or you can say, because 1 kilometer equals 1,000 meters, meters will cancel, and you get 6 kilo. Remember, kilo is 1,000. 6 kilometers. Some people say kilometers, but it's kilometers if you really think about it, because we use the unit as meter. So how did it become meter? But that's just the way the language tends to evolve. .76 milligrams equals 3.7 times 10 to the minus 3 grams, because 1 milligram is 1/1000th of a gram. And another way of writing 1 over 1,000 is if you take the 1 over 1,000, and the rules of exponent tells us that we could rewrite that as 10 to the power of 3. But what can you do with 10 to the power of 3? One of the rules of exponent says that if you bring the power from the denominator and you put it in the numerator, what happens to the power? What do you do to it? You put a negative sign in front of it. It's the same as this. You say 10 to the minus 3. Okay, so that's where I got the 10 to the minus 3. Okay? Then the sooner you become comfortable with the using of these powers and moving them around, you'll see that a lot of the stuff is easy. Because in science, they just take it for granted that you know how to work with numbers. And that's a bit of a stretch, because a lot of people don't know how to work with numbers. Some people are very weak in math. I'll even go so far as to say that even teachers are weak in math. You talk to most adults, their level of math is grade 9. Maybe. Most adults are around a grade 9 level of math. So now let's look at temperature. There's 3 temperature scales I'd like you to know about. There's more than one, but I mean there's more than 3, but the 3 major ones that are important are Celsius, Fahrenheit, and Kelvin. The Celsius scale is the metric scale, and it's based on a very simple assumption. They made 0 the melting point of water, and they made 100 the boiling point of water. So, and then they made 100 units between that. So we're all familiar with 37. That's temperature of our bodies in the warmest spots. Like if you take the temperature in the warmest spot of your body, like say under your armpit or in your mouth that's why they stick the thermometer under your tongue, because your body temperature there is as close as it can be to the normal body temperature. Normally your hands are not going to be 37. Your hands are going to be 37 if you're hot and your body's trying to get rid of heat, then the blood flow will go to your hands more. But typically your hands might be at 28 or something. Okay, so that's how your body controls the temperature. When you're warm, more blood flows to your skin to release the heat. When you're cold, the blood vessels to your extremities close and it pushes the blood back into your body to conserve heat. This is a typical mechanism. That's why when we get up in the morning, what do you do to wake yourself up if you're feeling sleepy? Cold water on the face. That actually stimulates something called the mammalian diving reflex. When you splash cold water on your face, it drives the blood to your brain and to your internal organs, and it actually pulls it away from your limbs, because your arms and your legs can do without, well, not do without, but they can go without blood for up to an hour. without damaging the tissues. So, you know, if you get your arm cut off, you go to the hospital, you bring your arm with you, right? And they can
Within an hour?
yeah, they can reattach it, and if you chill it, it lasts even longer. I've heard that with a kidney, if you keep it on ice, you can go up to 30 hours before you can't put it in the body anymore, because it'll start to decompose. Not decompose, but the cells start to die. But up to 30 hours if you keep it on ice. Now they have a new system where when they do a heart transplant, they actually keep the heart at room temperature, and they have blood flowing through it. So they keep the heart pumping, and they have a supply of blood going through it. And as long as the blood goes through it, then the heart can keep on going. I don't know how long it can go like that. Probably not, it wouldn't go for days, but the important thing is to get the organ in the best shape possible into the body of the person who's receiving it, so that they can then live a healthy life. Okay, so the first scale is Celsius scale. That's the metric one. That's the one we normally use in calculations. So the Celsius scale is based on the melting and the boiling point of water at sea level, because when you reduce the pressure on water, it actually boils at a lower temperature. But at sea level, which is, so melting point of water, we all know, is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. And then the Celsius scale, you see, is based on this 100 gradations. The Fahrenheit scale was invented by somebody who basically, it was the smallest increment in which he could feel a difference in temperature. So it's based on 32 as the melting point of water, and 212, I think, for the boiling point. But it's not you know, it's based sort of in the middle of nowhere. 0 and 100 is a much nicer system. But we should know how to convert from one to the other. And more importantly, we should know, we should understand what the Kelvin scale is. The Kelvin scale is the same as the degrees Celsius, except they made 0 of that scale equal to the lowest temperature you can reach in the universe. The coldest you can go in the universe is something called absolute 0. So that's, sorry for not turning. The lowest temperature you can reach in the universe is 0 degrees Kelvin. That's minus 273.15 degrees Celsius. So let's write down some conversion factors based on that. Kelvin is equal to the degrees Celsius temperature plus 273.15. So that 0 degrees Celsius equals 273.15 Kelvin. And 0 Kelvin equals negative 273.15 Celsius. And it equals absolute 0. So you can't get colder than that. Kind of a hard thing to imagine, but there's a certain temperature at which there's no more heat energy, so you can't get any colder. You can only get, it's like darkness. How dark is dark? Well, if you turn off all the lights and you put plastic garbage bags on the window and you block out every little bit of light that comes in, that's total darkness, right? Actually, strictly speaking, that wouldn't be total darkness, because if you're warm, you're giving off infrared light. But we can't see infrared light, so for us, that's darkness. If you had a pit viper can see infrared. So in a totally dark room, a pit viper, which is a type of snake, can see a rat scurrying by in the dark, and you know, have lunch that way.
So do you really think we can explore space when we don't even know what's deep in our ocean?
can, but it's risky, right? People die all the time because of, we can do it if we put an effort into anything, we can do it. We've been to the bottom of the ocean, and, but there actually been fewer people in the bottom of the ocean than there have been in space, on the moon. If you go to the very bottom of the ocean is 7.5 miles down. So it's not a very hospitable environment. The pressure down there is something like 14,000 pounds per square inch. Think of your thumb, the size of your thumb, there'd be the weight of 3 minivans on your thumb. That's the pressure at the bottom of the ocean. So whatever you go down there with, it's gotta have windows and the outside sort of, the outside hull of the ship that you would go down there would have to be made of foot-thick steel, because otherwise you'd get crushed. The windows on those things are about 8 inches thick. They're like made of quartz, the hardest type of glass you can get. Anyway, absolute zero is the coldest temperature you can get to. Can't get colder than that because there's just no more heat to give up. It's impossible to get a lower temperature than absolute zero, because there is no heat left. It's just like, it's like light. If you get to a place where there's absolutely no light, then it's total darkness. And darkness is not really a thing. It's just the absence of light. You can't go to Walmart and buy a dark bulb. You know, you plug it in, it makes the room darker. You can only buy light bulbs. And light and darkness is simply the absence of light. Also, if you want to convert between the Fahrenheit scale that wasn't mine. I may have misspelled Fahrenheit. That extra H in there. The Fahrenheit scale is based on 9/5 times the degree Celsius temperature plus 32. That's going to give you the Fahrenheit temperature. Or if you like, if you want to go the other way, multiply the Fahrenheit temperature minus 32 times 5/9 is going to give you the Celsius temperature. Example. What is the temperature in degrees Celsius if it is 95 Fahrenheit? So you would say, you want to go from Fahrenheit to Celsius, so you're going to use this formula. So you plug in the Fahrenheit temperature here, subtract 32, multiply by 5/9, and you're going to get the Celsius temperature. What you have here, therefore, is 95 minus 32 times 5/9. That's going to give you the Celsius temperature. What you get is 35 degrees Celsius as your temperature. The sun's core is believed to be 15 million degrees Celsius. That's where the temperature where nuclear fusion takes place. What happens is hydrogen nuclei, stripped of their electrons, can bump into each other and form form helium nuclei. That can only happen at extremely high temperatures. Hi.
I'm so sorry to interrupt.
No problem.
Is it possible, when you have a break, which one that we, I just need to speak with Aaliyah, is she here?
Is Aaliyah here? No.
Has she been to Moses?
I can't
Does
remember. to
anyone
be
know
honest
if
with you. I don't
she's
know.
been here? Aaliyah? She hasn't been here? Okay, she hasn't come to my classes either, I just need to try to sign in, I'm so sorry to
No
interrupt.
problem,
I
no
was just
problem.
hoping to try to
Okay,
figure it out. Okay, if I find out anything about it this year, then I'll let you know.
thank you.
Have a great day.
You too, bye. So the core temperature of the sun is 15 million degrees Celsius. That's the temperature at which these nuclei can be smashed together to form bigger nuclei, to form helium. So the sun is steadily turning its hydrogen into helium. And it's a frightening figure if you look at it. 4 million tons of hydrogen are converted into pure energy as well. Some of the mass of the sun actually disappears every second. The sun is getting 4 million tons lighter every second because of something called mass defect, where some of the matter turns into pure energy. And that sounds kind of scary because, oh, is the sun going to disappear? No, well, yeah, it will eventually get small enough so that it stops being able to convert hydrogen into helium. Also, it's going to run out of hydrogen. That's going to take about 5 billion years, though. But then when that happens, the sun's going to start shrinking.
Would it explode at the end?
It won't explode, but what'll happen is it'll shrink, and once the shrinking caused by gravity gets big enough, I mean, when the pressure gets high enough at an outer layer in the sun, it's going to reignite the nuclear fire, and then the sun's going to get really big, and it'll reach up to the Earth. So it'll swallow up the Earth. We'll be inside the sun in 5 billion years. But hopefully we won't be here anymore, so it'll be okay. I don't plan on living 5 billion years. That would be horrible.
Do you think that when the sun is shrinking, we're gonna lose more heat, and then
Yep.
by that second, you're gonna be really cold, and then
Yeah, I think the Earth is going to get pretty cool by the end of the sun's life, and but it'll take billions of years. The sun has been cooling since, you know, even hundreds of millions of years ago. If you look at the Earth back in, say, during the Cretaceous period or the Jurassic period, which was 100 million years ago. So the Cretaceous ended 65 million years ago. That's when all the dinosaurs died. But they didn't die because of the sun. They died because of an asteroid hitting the Earth. And it was so big that it made a giant cloud of dust, and it made a giant cloud that blocked out the sunlight long enough that a lot of the plants died. And then when the plants died, the herbivorous creatures died. And then when there were no herbivores, the carnivores died. So all the big animals died. Only the small animals that didn't eat too much food survived. So the Earth was repopulated in the millions of years that followed by new species. But what's been obvious in the archaeological record, if you look into it, and it is interesting, every so often there's a huge cataclysm that kills a whole bunch of animals. And we even had one pretty recently, because the Earth used to have giant sloths and woolly mammoths, and then they all died all of a sudden. It only happened like 15,000 years ago. So some people say it was caused by the Ice Age, but I think they're putting the cart before the horse. It wasn't that the Ice Age killed the animals, it's that there was a sudden change in the climate, very, very sudden change in the climate that even caused the North Pole to be in a different place on the Earth, and it made the equator be in a different place on the Earth. So Canada became like the tundra. Where we are now used to be covered under 2 miles of ice. It was literally 2 miles of ice here, and then it melted, but it took thousands of years. That was the last ice age. But the mechanism as to why the Ice Age happened, that's not clear yet. I don't think scientists really understand how the Ice Age happened. Some scientists say it has to do with cycles in the sun, because there's different, you know, the Earth has tilt. It also changes its distance from the sun over periods of thousands of years, and the sun's brightness does change over the course of thousands of years. If all those cycles were to line up in a cool period, if all those three things line up, you could have an ice age. That's what some scientists say. But I think it's even more dramatic than that. Some scientists have begun proposing a theory that the Earth literally undergoes a pole shift. Like the North Pole becomes the South Pole inside the Earth. So the magnetic field shifts around so much that it literally causes the crust to change position on the Earth. And and there's evidence of that in the geological record. When rocks are melted and they cool down, they cool down in the same direction the magnetically sensitive rocks line up with the Earth's magnetic field as they're cooling off. So they've found records of of rocks on the Earth that have their magnetic field lines in opposite directions to the normal direction, which means that at some point in the past, the Earth's North Pole was in a different place, which is freaky. Imagine the North Pole changing spot, by thousands of miles. That would have a big effect on climate. So, yeah, I don't think they've figured it all out yet, but there is evidence that some dramatic climate changes happened in the past, and it was not caused by human beings. Because nowadays we're all seeing this narrative, carbon footprint, and they make you feel guilty for breathing. But I don't think human beings have that much of an effect. We have some effect, like we increase the CO2 levels, but CO2 is only a small part of the picture. It's a small part of the equation. In the past, when the dinosaurs were on the Earth, and even before the dinosaurs were on the Earth, the CO2 levels were 15 times what they are now. 15 times. Okay, so the Earth didn't end then, and it's not going to end now, at least not the way we think. The Earth has gone through tremendous climatic swings. What's the worst that could happen? If the ice caps melt, what's going to happen? The oceans will come up, and your condo in Florida is going to be underwater. Oh well. But it's not going to happen overnight. It's going to happen so slow enough that you're going to see, we don't have a backyard anymore. What happened to our backyard? You're going to have to move away, but it'll be over the course of decades, if not centuries. So I think the whole climate change narrative is actually a form of political manipulation. They're just getting people scared so they can get power for themselves and make you pay taxes, more taxes. Like at Home Depot, they included a new tax for disposing of chemicals. Disposal tax, carbon tax. Bottom line is people taking money from other people. That's what it really is. It's not about climate change. That's my opinion. Feel free to reject it, but you have a right to hear it. Okay, now we'll go over here. One of the commands that we received from God right at the beginning of the earth, when human beings were speaking to God, his command was, be fruitful, multiply, fill the earth, and subdue it. What does that mean, subdue? When you subdue someone, what does it mean? Conquer. You bring them under control. God's command to man was, be fruitful, multiply, fill the earth, and subdue it. In other words, you should be able to drop me somewhere, anywhere on the earth, and I would not be in danger of dying. That's the earth subdued. Okay, drop me in the middle of the Sahara now, I'm dead. Drop me on the top of the Sierra Nevada, I'm dead. Drop me in Patagonia, I'm dead. There's many places on the earth where if somebody dropped you off, you'd be dead in a matter of hours at that. So the earth is far from being subdued. One of the biggest and most unbelievable hoaxes that I've seen is the people talking about water shortages. The only place you should be having a water shortage is in the desert. If you live in Las Vegas, I believe it is possible to have a water shortage because you've got to purify the water that you get. But we put men on the moon. We can't figure that out, how to bring some water from somewhere else, or find some system where the water is purified from the ocean or something. No, Las Vegas is right on the, it's very close to the coast. Well, not very close, it's a few miles inland, but they could make an aqueduct, they could make ways of extracting water from the air. They figured it out in Saudi Arabia. It takes money, basically. It takes a lot of money. In places like, in the desert, in places like Saudi Arabia, what do? They have petroleum money. They desalinate seawater. They use reverse osmosis or just plain pure distillation. A lot of what we think is manipulated. You know, for instance, when you buy water from those bottles, you know, those big carboy bottles, the blue ones that hold about 5 gallons of water. And, you know, they always have a nice picture of a mountain spring with, you know, a stream coming down to make it look like, oh, it's from a spring source. I happened to work in one of those water bottling plants here in Toronto. I saw every different type of bottle. It all came back to the same spot, and they refilled it. You know what they filled it with?
Filtered water.
Tap water that's been boiled. So they put a nice label on the bottle, but it's all a lie. It's tap water that's been boiled to leave behind the impurities. Water's pure. It's good water. Don't get me wrong, but they create this picture of spring water, but it's distilled.
Morning, sir.
Good, thanks. You want the attendance?
Yes, please.
All right.
Thank you. Take care.
You too. So again, you want to convert Celsius temperature into Fahrenheit. That's the Celsius temperature. Multiply by 9/5, and then you add 32. I forgot to write the plus 32. And there you go. There's your temperature. And then of course you can report it to 2 significant figures because that's what we started with anyway. In practice example, on page 16 of this textbook, it asks, ethylene glycol, the major ingredient in antifreeze, freezes at minus 11.5 Celsius. What is the freezing point in Kelvin and in Fahrenheit? Let me show you how that works. Practice example on page 16. So it freezes at negative 11.5. If we add 273.15, we can convert it to the Kelvin temperature at which it freezes, 261.65 Kelvin. If you take that 11.5, negative that is, and you subtract 32 from it, multiply by 5/9, you find out that it's a negative 24 degrees Celsius. The interesting thing about the Celsius and the Fahrenheit scale is they meet at minus 40. When it's minus 40 Celsius, it's also minus 40 Fahrenheit. They're different sized degrees, but the scales they have their zeros at different spots, so they meet at a different temperature. But minus 40 in both Fahrenheit and Celsius, it's the same actual temperature. Now, I want to take on how we work with length, area, and volume, because it's an area where a lot of students have trouble dealing with the numbers. What is length measured in? What's the favorite unit for measuring length? No, that's area. Length is only one dimension. You're just measuring, like from here to the door, how many meters? Let's say about 7 meters, right? So length is measured in just meters. Area is length times width, so it's going to be in meters squared because you have 2 dimensions. And what if I want to measure volume? How many dimensions in volume? It's cubed, so it's 3 dimensions, so it's meters cubed. Okay, so always keep in mind that when you have one of these measurements using these 3 different quantities, you need to use the appropriate units. So let's do an example. Convert 15.3 meters cubed into decimeters cubed, kilometers cubed, centimeters cubed, and millimeters cubed. And we could also convert 15.3 meters squared into all of that. And we could also try 15.3 meters in all of that. Let's start with the easy stuff. Let's start with the linear part. Linear part is very easy. So for linear measure, if you have 15.3 meters and you want to convert it into decimeters, the conversion factor is that there's 10 decimeters for every 1 meter. So it becomes 153 decimeters. Notice how meters will cancel. If I want to go to kilometers, 15.3 meters times 1 kilometer for every 1,000 meters means you're going to have 15.3 divided by 1,000, which is 0.0153. I moved the decimal 3 times. 1, 2, 3. Yeah, that's right. That would be in kilometers. Continue writing up here so we don't move the camera. If I want to convert 15.3 meters into centimeters, I'm going to say there's 100 centimeters per 1 meter. So meters cancel and I get, add 2 zeros to that. Or move the decimal over, well, I could say 15.3 times 10 to the 2, because that's what 100 is actually. And then I can turn that into scientific notation by moving the decimal over by 1, which means I have to make this power 1 higher. So that's what you get as an answer for centimeters. And if I want to convert 15.3 meters into millimeters, what was the last one? Okay, meters cubed, it doesn't apply for that because it's the same unit. So now let's go to area. Let's work with area. 15.3 meters squared. So that means that whatever the dimensions were, say you had 2 times 7, you get 14. So whatever it gives you, whatever multiplies out to give you 15.3 but meters squared. Now we want to convert it to decimeters squared. So you're going to use the same idea. There's 10 decimeters in a meter, but remember that it's got 2 dimensions. So now your conversion factor also has 2 dimensions. You get to raise it to the power of 2. Now watch this. When I have something raised to the power of 2, and there's a bracket around the thing that I'm raising to the power of 2, that power of 2 applies to everything inside the bracket. Okay? So let me rewrite that bracket with the power distributed into it. What's 10 to the power of 2? You could just write 10 to the power of 2, right? 10 squared. What's dm squared? Just put dm squared. What's 1 to the power of 2? What's 1 times 1?
1.
Still 1. And finally, meters become squared as well. Now look at this. You can cancel the meters squared. And 15.3 times 10 squared, you could just write 15.3 times 10 to the power of 2 decimeters squared, but then you can simplify it to scientific notation by moving the decimal over by 1. 1.53 times 10 to the power of 3 is your answer, decimeters squared. Okay? Notice I have not used the calculator because I know my powers of 10, which is what I'm trying to get you to do as well. So I said, what are the different conversions? Let's write them at the top so I don't lose track. Decimeters, kilometers, centimeters, and millimeters. All right, the next one is kilometers. I want to convert 15.3 meters squared to kilometers squared. I know that there's 1 kilometer for every 1,000 meters. But our conversion factor has to be raised to the power of 2, because it's length times width, right? So let's rewrite this conversion factor with the 2 distributed in there. So you could get 15.3 meters squared times 1 squared, which is still 1, kilometers squared, over 1,000 squared. What's another way of saying 1,000? To make it more compact. 10 to the power of 3. Okay, good. So 10 to the power of 3, but now you're squaring it. What's 10 to the 3 raised to the power of 2? Remember the rule of exponents? When you raise a power to a power, what do you get? No, you don't add them in this case, you multiply them. When you raise a power to a power, you multiply. Yes, it becomes 10 to the power of 6. So what you do here is you rewrite this as 10 to the 3, then raise it to the power of 2, so it becomes 10 to the power of 6. And then meters is squared. Notice I'm not using the calculator. No calculator is necessary, because I'm just working with my little rules of exponents. It makes it so much easier and faster. It's faster than a calculator, because you end up being able to do it in your head. And then the meters squared cancels, okay? Which is what you're trying to do in the first place. And now you can say 15.3 kilometers squared, 15.3 over 10 to the power of 6 kilometers squared. Are you satisfied with that answer? No. What else can you do? You got 10 to the power of 6 in the denominator. What happens if you bring it up to the numerator? What happens to the power?
10 to the negative.
Right, it becomes 10 to the negative 6. So you become 15.3 times 10 to the negative 6 kilometers squared. You're almost finished. You want to put it in scientific notation by moving that decimal over by 1. So you can say 1.53, and because you made this 10 times smaller, you're going to make this 10 times bigger by raising the power by 1, so it becomes 10 to the minus 5 kilometers squared. And you're done, and you haven't used the calculator at all. And to somebody who's not familiar with this technique, it'll seem like magic. Because most of the time, like I said, people are operating at a grade 9 level of math skill, and they're completely at a loss for how to do these kinds of calculations, but they're actually quite simple. You just have to know your rules of exponents. This is what in my opinion, this is what turns most people off on science and math. They just have a couple skills that they're not good with, and then nobody ever taught it to them, so they just go, I hate science. Actually, there's room to do one more down here. So I have 15.3 meters squared. Now I want to convert it into centimeters squared. So the conversion factor for linear, you always start with linear and then put the right power on it to adjust it. What's the conversion factor from meters to centimeters? How many centimeters are in a